All right, we're going to solve trigonometric integrals and see what is the main caveat when it comes to trigonometric integrals. Important question to answer first is this one. Which integral do you think will be easier to solve? Cosine raised to the 8th power or cosine raised to the 8th power when it has its buddy sign next to it? And this integral is so much easier to take because, this doesn't just apply to this type of integrals, trigonometric, but anytime you have integral where you have a derivative of a term sitting next to it, those are easy integrals to take. What I mean by that is that derivative of cosine is negative sine, right? So I have du supplied in the integral sitting there. That's convenient, and this integral is basically going to be a basic power rule, right? So you just take this integral negative there. That would be the answer. You would back substitute, of course, but get solved in one line. On the other hand, this integral is extremely involved, and the solution would take you probably 3 pages. Before we discuss cosine raised to the 8th power, let's see if we can solve cosine squared. So in this video, we're going to solve these 4 problems right here, but I'm also going to talk you through some of the other integrals like cosine squared. Okay, so cosine squared x dx. This integral is not too complicated to take because you use power reducing formula. If you don't remember, you can look it up. And then you're in effect taking this integral. You separate the numerator and you take this integral and this integral. A little use up there, but not too big of a problem. Cosine cube x, that's an odd power. And usually what you're going to be doing a whole lot in this trigonometric integrals section is whenever you have odd power, you borrow one. So you take one out and then you are left with even power, right? Because if you take one out of an odd number, you're going to be left with an even number because odd numbers are nothing but even number plus 1. So this is done in order to get this cosine written in terms of sine square x, which comes from this Pythagorean theorem written in the language of trigonometry. This is Pythagorean theorem written in terms of x and y. This is Pythagorean theorem written in terms of cosine and sine. And this enables you to express sine square x as 1 minus, because you move this, right? Cosine square x. And then sine square x is expressed in terms of cosine, or you can express cosine square x as 1 minus, you move this, sine square x. So in this way, you can move back and forth between cosine square and sine square, whichever suits you best in that problem, whatever makes your solution easier. That's why you do that. So that formula that I just showed you is going to be used over and over and over again in this section of trigonometric integrals. Here we utilized exactly that. You see cosine square x written in terms of sine square x, and this one cosine is tucked away, put away, to be used as du. And that ended up as a basic power rule again. All of these integrals are going to end up being power rules that we're going to solve today, those 4 integrals. Then getting closer to cosine raised to the 8th power, but we're not there. We're now working on cosine raised to the 4th power. It's already getting a little bit, solution is getting lengthier and a bit more involved, okay? Here, you again use that power reducing formula, but here you have cosine squared times cosine squared, so you have to take square of that. So then you do this, and then you have to use another power reducing here. So it's getting involved. It's doable, but there's this very convenient formula. Whenever you have cosine raised to some higher power than 3, because 3 you can do it without too much issues, and also square you can solve that without too much labor. But when it's already raised in the 4th, 5th power, and it doesn't have its buddy sine with it, you use this extremely convenient and beautiful formula, John Wallis's formula for cosines. And an interesting thing is that John Wallis's formula works for sines as well, and you can actually prove that. There are tons of videos on YouTube that go through the proof. I will actually include one in the description below, because I really like that video. But this is a lovely project if you have to do a research project or a project in your calculus too. John Wallis's formula would be lovely, because in recent times, in 2015, there was a connection found between quantum physics and John Wallis's formula. Physicist Carl Hagen and Tamar Friedman, who's also a mathematician, found a connection. And they actually stumbled upon Wallis's formula as part of their calculations when they were solving for gamma function, when they were observing high energy state of hydrogen atoms. So in 2015, the internet exploded. There were tons of papers that came out that John Wallis's formula found in real natural world, in reality, in the quantum mechanics portion of reality. And because universe reveals itself through mathematics, and sometimes we're lucky enough to catch that, and it is absolutely moving and beautiful. 1655 is when John Wallis came up with the formula for pi, and that's what you would look up. You would look up a formula for pi. It's an infinite product, and it was 18 years before Leibniz's formula for pi. It was before calculus, right? 1655 is before calculus was developed. So lots of good inspiration for your research projects, maybe. And even maybe for not just calculus too, but in your physics classes as well. So here, we're not going to be solving this, and you use Wallis's formula whenever cosine is raised to some obnoxious power, or sine is raised to an obnoxious power, and they don't have their other buddy next to it, right? But here we do have the pair presented together. So that's what we're going to use. For the first two, we're not going to use this guideline because we don't need to. But in the second, in the third, and in the fourth examples, we are. But you're going to also see by solving first and second problems first that this guideline is nothing but something that you would do naturally anyway, because it actually makes sense. This is not some type of a new formula or life-changing formula that usually you learn a lot of important life-changing formulas in your calculus classes. This is just a guideline, nothing fundamental or new about it. I'm going to just start solving it. The first problem, this one, is there are 3 different ways to solve it. You can use the double angle formula of sine, but I'm not going to do that because I really want to showcase this idea that cosine and sine, whenever they're together, they gave you u times du, which is, and that's what I want to, that idea is what I want to use. Now you can choose cosine to be u. In that case, negative sine x dx will be du, but I don't want to deal with negative sine, so I will choose that sine is my u, because sine's derivative is cosine x dx, and I don't need to worry about minus signs. I will rewrite this integral as a u sub. And this is power rule, very simple power rule. You back substitute. U was sine, so sine squared. This is your final answer. All of these integrals, you can count on them turning into power rules, all of these. Now this one is also already ready for the u sub, and in this case I'm going to make sure that u is the one that has the highest power, which is cosine, and I'm going to have to deal with negative sine, which derivative of cosine will bring negative sign, but that's fine because I can multiply both sides by negative. This side will turn positive, and I like to express exactly what I have in my integral so that I can say this equals to du u cubed negative du. Negative comes in front, and then I take the integral of u, and that's basic power rule as promised. Last thing left to do is back substitute. This time cosine was our u. And that's the final answer. Now, in the third and fourth examples, I am going to use this guideline. And the guideline says this: anytime you have odd power of cosine or sine, so it cares about the odd powers. It wants you to do something to the odd powers of cosine or sine, whichever has odd. In our case, cosine is the one that comes with odd power. In first case, cube. In the second case, power 5. So we're going to do things to cosine. And what you do, the guideline tells you, is to save one cosine for du, and then you'll be left with even cosine to raised to the even power, right? And you'll see why we're going to do that. So I'm going to rewrite this. I'm going to borrow 1, and I'm going to have square here. So in this step, I'm simply rewriting cosine cubed. It's cosine times cosine square x. And this I left unchanged. The guideline doesn't want you to do anything to the one that came with the even power. And now I'm going to express cosine square as, in terms of sine, as 1 minus sine square. Usually this cosine, as we said, we're going to keep that for and tuck it away for du. So I'm going to write that next to dx. It's not essential, but I think it kind of keeps things organized. Now, you're going to multiply this term through, and you're going to have 2 terms being added or subtracted. And at that point, you can always separate. Whenever you have sum of the terms in integral, you can take integrals and then sum them. That's what I'm going to do. So first, sum or difference, it doesn't matter. And then second, and I'm going to add powers of sine, and that's going to be 6. By the way, a fun historical fact: before parentheses were used, there were these over bars, not under, but over bars that were used as parentheses. That's how Leibniz wrote in his notes. It's maybe more convenient if you're writing in pen, but less convenient if you're writing in, if you're typing. So we're going to do a u sub. Both integrals are going to have the same u. This is how it's going to always work out with trigonometric integrals of this sort. Usually you're going to have 2 or 3 integrals, 2 or 3 terms being added, and u will always be the same, either sine or cosine, for both integrals. And then du, do you see how conveniently each integral has its du sitting next to it? That's why we did all the things that we did, so that we would accomplish exactly that. Because anytime you manage to have u times du, that's one of the best and most easy intervals to take. Now, don't forget the power, that in the first case, sine is raised to the fourth power and sine x is my u. And in the second interval, it is u power 6 du. I know how to take these intervals because these are basic power rules. I'm going to back substitute. In these intervals, it's always going to be the case that whichever has the odd power will not be the u. So in this case, cosine is going to be part of the du. So it can't be u. What's going to be u for this interval is the one that came with even function. And that's exactly what happened. Our u was sine x and du was cosine x. And initially, remember we took out 1 cosine x from cosine cube to put that away for du. So now solving this interval, it's very similar, but now we have it raised to the 5th power. First step is going to be the same. I'm going to borrow and take out 1 cosine, and I'm going to have cosine raised to the even power, in this case 4th power. And now I'm going to write this not as raised to the 4th power, but square and square that, which is same as cosine raised to the 4th power. It's just a different way of writing that. And I think it's best to write it like that. And why did I do that? Because I have a formula that connects cosine square to sine square. And that's what I'm going to do. Again, these first 2 steps are the same. This is exactly what I did in the previous example. Oh, can't forget that. Okay, now I'm going to write this cosine with dx, because I'm going to tuck that away to be used as du in a little bit. The reason why I'm doing this example as well is because there's this little thing here that in the previous example, we just had this expression and we multiplied it through. Here, we can't. First, we need to raise this to square. We need to expand it and do the binomial, and then we're going to multiply it through. So here, square x plus sine raised to the 4th x, and then now I'm going to multiply it through. Instead of 2 terms, now I'm going to have 3 terms. So I'm going to split that into 3 intervals. Oh, and I'm going to multiply it through by 1, by negative 2 sine squared, and positive sine raised to the 4th power. First interval will be just this thing by itself, because it's multiplied by 1, minus 2. I'm going to bring out of the interval because that's constant and I can always do that. I'm going to add powers of sine. Here I'm going to have 6. Are you looking at how each of the all of the 3 intervals are going to get their very own cosine x dx? That's the whole point of this trick or guideline. Now I'm ready for the u sub. So you don't have to write a u sub in this case, because you know that whichever was in the even power, which was sine, and whichever you didn't tuck away for u, which was cosine, is going to be your u. So sine is going to be my u, and this is going to be du. And whenever sine is u and cosine du, you don't have to account for negative sign. So maybe you skip the u sub and you just write the answer. you treat sine as if it was u, and you just treat it as power rule, because you have u raised to the fourth du. So increase power by 1 over 5 minus 2 sine raised to the 7th over 7 plus sine raised to the 9th over 9. That's the final answer. So that guideline that you have is not a new formula. It's actually something that you would want to do anyway. It makes sense to do it because whenever you have odd power of cosine or sine, you want to keep one of that for the du and turn that into the other, which is sine square x in case of a cosine. And as you can imagine, sine and cosine have this type of dance between each other, right? Because they're each other's derivatives and each other's integrals. And secant and tangent have a very similar types of problems, which is coming in the next part. So these are trigonometric integrals that utilize this guideline. So I hope that this was helpful.